Today is Thursday, 23rd of December. There are two things that I need to do. First, I would like to comment on the evaluation, the quiz that we gave you last Monday. Then the next task in this class is to start thinking about or completing the final project, okay? So the first thing that we have to do is to assign the themes, okay? The structure that you have to analyze to each group. So that's something that we need to do. And today we're going to do the random assignment of each of the structure to each group. And after that, basically we have to wait a couple of days until Engineer Isaac prepares the information for each group and send it to that group. Okay, so that's about for today. It's a short session since we had already two, right, activities this week. So we have the quiz and we had the presentations. So basically this is a short session in order to complete the second hour. Okay, so a couple of persons after completing this and the quiz told me that they thought it was kind of long. Here I have the first question. Can you see the question one, people? Can you see question one?
Yes, doctor.
Yes.
Okay. Mr. Wacon, could you please read the question?
No, doctor.
Can you read?
Oh, yes. Using one bin finding element, calculate and plot the bending moment distribution for a 2 meter long steel beam. When a concentrate the force F is acting downward at X, same L.
Just L/3, okay? Now,
Yes.
is there any problem with that information? Okay, is there any problem with that information? I don't think so, right? It's quite clear. We have a beam with a concentrated force at a certain point, and the force points downward, and that's it. Okay, let's continue. Mr. Wacon, please go on.
Yeah. Left end is clamped and the right one is guided. You know,
Guided.
Guided.
Okay. So there are the two boundary conditions. It says clearly that the left is what? What's the condition?
Guided.
No, the left.
Is displacement.
No.
Zero.
What's the support on the left of the beam, Mr. Wacon? What's the support?
It's clamped.
Clamped. How about the right?
It's guided.
Guided. Okay. So what do they ask you, Mr. Here it is. Genesis is going to help me. Okay. So I'm asking you to prepare and plot, okay? Not only deduce an expression, but also plot the distribution of bending moment of a beam, one single beam, with a concentrated force. Okay. I just want you to tell me more or less how can you describe the deformed profile of this beam? Somebody? Mr. Ramon, could you describe the deformed profile of this beam?
The deformer, I in my case I discretize the deflection.
Yeah, but can you describe the deflection, the deformed?
Yes.
How do you start on the left?
In the left is clamped, right? In X and Y is 0.
What is 0?
Because
No,
it's clamped.
not why. What is 0?
The displacement in X and Y direction is 0.
Is that all? The displacement is 0?
Yes, in left and in Y only.
No. On the left. What else is 0 on the left? Miss Sayo. Miss Sayo. What else is 0 on the left end? Miss Sayo.
Good morning, doctor. What
is?
age?
No, okay, no. The question is, Mr. Ramon says that the deflection or the displacement on the left is 0 in the X and Y directions. My question is, what else is 0 on the left of this beam?
The angle, doctor, no?
Exactly, the slope. So you have 0 deflection, 0 slope on the left. And what about the right one, Mr. Barba? What can you say about the right end of this beam? Mr. Barba, are you there?
Is guided.
Yeah, so I can read. The thing is, what does that mean physically to you?
Yes. In the boundary condition is the first derivative is 0 and the force is 0.
What force?
And shear force.
Exactly.
Yeah.
So there you have it. So you can describe the deflection. Okay, let me try. Okay, so can you see what I'm writing, people? Can you see what I'm writing? See, I'm going to write a beam. And a beam. Okay, I'm going to write a beam. Okay, so this is my beam. It's clamped on the right, guided. We have a force here. I don't know, for some reason it doesn't like to write. Okay, now My question is, how do you describe the deflection? And we see that if we have this this force here, so we start at 0 here, as Mr. Barba said, Mr. Wacon said, 0 slope, and then we go downwards, and down here, we end up with 0 slope also. So what do you expect for the bending moment, Mr. Jimenez, of this beam? What do you expect for the bending moment? So this is the deflection here. That's it. Okay. Mr. Jimenez, what do you expect for the bending moment?
You hear me, doctor? Doctor,
What-
can you hear me?
Yeah, I can hear you. For example, on this part, okay, for example, in this part, what type of bending moment do you expect in this part, Mr. Jimenez?
Direction counterclockwise.
What is not? What is the bending moment in this area? Positive or negative?
Positive.
Do you agree with that, Mr. Nevares?
The reaction or the equivalent?
No, I'm talking about the bending moment, people. Come on, don't make me waste time.
The reaction, positive.
No, I'm talking about bending
Negative.
moment. That's what.
Negative is for the first in.
Why you say it's negative, Mr. Nevares? Why you say it's negative?
As a positive.
Why you say it's negative or positive? That's what I'm asking.
Because for static.
No. Anybody? Why you say the bending moment in this area is going to be negative?
Or, doctor.
What?
Or it's somewhere on the
In the
right, the down.
Why you say that in this area, the bending moment you expect to be negative? Mr. Ruiz, why do you expect in this area the moment to be negative, the bending moment to be negative?
Good morning, doctor. For definition, the bending moment is negative of the shear force.
And oh man, we're in trouble. People. When you have a sad beam, the bending moment is negative. In this part here, the bending moment is positive because in this part here, you expect the beam to be smiling. Smiling beam. Okay, so we have a general idea. What do we have to expect about the answer? So we know that in this part here, we expect the bending moment to be negative. In some part here, there will be a changing sign. And on this part, we have to have, or we expect the bending moment to be positive. And we have done nothing but remember what we did in solid mechanics and in ship structure. Oh man. Are you going to tell me that this is very difficult?
You could not use the right hand in this area.
The right hand? What do you mean by right hand? I don't understand what you mean. What do you mean by right hand? I don't
It's
understand.
the rule. The rule.
The rule of what? The rule. I don't understand what you mean. Anyway, let's do this, okay? So you have this, and what I'm asking now is, we're going to do a short survey, okay? So I'm
You're
going
not
to,
sharing.
yeah, I know. I'm going to ask you to complete a short survey on this problem, okay? And then let's see if it works or not. So there are very short questions, and this is not graded, okay? I just want to give you the message that it's just a matter of thinking, okay? So please try to complete in the best that you can this short survey. Okay, I'm going to launching. Do you see the survey, people?
Yes, doctor.
Yes.
Okay,
over
please
the screen.
complete it. Okay. Please complete the survey. It's about this problem. The first
This is
question is
about the first question of the exam.
exactly. That's what you see up in the title. You see it's finding element beam bending, short review. And this is the first question was related to beam bending, right? Okay, please, come on. Let's work. So in the first question, you have to write the load function, okay, which is acting on this beam. Okay, the load function, that's P of X. Okay, P of X has units of force per unit length. That's what you have to write. Mr. Carrillo, did you complete question 1?
Yes.
Okay,
Yes,
good.
I have it writing variable.
No, don't write it. Don't tell me because we don't want
Okay,
to
no
tell
problem.
the other students about it. Thank you. I just wanted to
I
check.
write, it's necessary writing the range. Length.
Exactly.
No problem.
Exactly.
Okay, no problem.
Good. Mr. Galarza, are you in the second question or the first question, Mr. Galarza? Mr. Iñiguez, have you completed any question, Mr. Iñiguez? Mr. Iñiguez, are you there? Mr. Iñiguez?
Yes, doctor, yes, yes.
Okay. Did you answer question 1?
I am writing right now.
Okay. Mr. Galarza, are you there? Mr. Galarza? Mr. Carrion? Are you there?
Yes, doctor.
Did you answer question 1 and 2?
I'm asking question 3 now.
Okay, good. See that 8 people have answered question 1.
Doctor, it's only 4 questions in one row, or there are more rows? I can see.
There are 4 questions. 4 questions. Did you complete it?
Is it a single row, no?
Yeah.
Okay, yes.
See that only 8 people have answered question 1, and you are 11 people. So there is somebody in the waiting room, Genesis.
She is entering.
Okay, thank you. Ms. Lopez, good morning. We're doing an exercise here. No points. It's just a check about the first assignment, the third evaluation, the third quiz. And I'm asking you to complete this short survey. There's no points for this, don't worry, but I need you to answer. So in a few minutes, we're going to do a session where we're going to discuss as a group all of these answers, okay? Ms. Lopez, did you understand what I said?
Yeah, good morning, sir. I have the quiz to show the view.
Exactly. Please try to complete it as soon as possible. Okay, please raise your hand once you complete it, okay? Because we don't have I want to complete this in 1 hour only. The whole activities. So please raise your hand if you complete all the assignment, all the quiz, all the poll. I see that some people have done it. Once we get 60% of the class, then we will go on. So 60% of the class is what? 12, so 7 people. Once we got 7 people who completed, we will go on with the comments on the correct solution. Please raise your hand after you complete it. One more people. We need one more. Mr. Ordóñez, did you complete it?
Good morning, doctor. Yes.
Okay, please raise your hand. Okay, you did it. 3, 6, 3, 6. Mr. Wacon, did you complete? Did you finish?
No, Doctor, no complete is the one question. No.
Come on, it's not so complicated. It's so easy. Okay, asking you now is to share your answers. Okay, so for example, can you describe the load function acting on the beam? Somebody? Mr. Jimenez, can you describe?
It's a force minus F delta function x minus L over 3.
That's it.
Yes.
That's it. Okay, so you have a concentrated force. So the P of X is just minus F delta X minus L over 3. That's it. Okay, now let's go on. In the next question, I'm asking you, okay, what's the degree of freedom of a joint that needs to be calculated? What's your answer, Mr. Nevares, in question 2? What's the degree of freedom that you need to calculate?
And to calculate the reactions, no, the displacements are zero.
No, please, degree of freedom. The degree of freedom of the joint, what it is either motion, displacement, or rotation. That's what I'm giving you: displacement, rotation, displacement, rotation. Of those four,
it was phi, no F.
No, it's phi. If I write you, see, these are little things. I know I make many mistakes, but I try. In class, what we have said about the difference between little f and large F and capital F. We have said that when you have a force, we use large F or capital letters in general.
Yeah.
But we use little f when we want to express force per unit something. So this is phi. Mr. Ordóñez, what did you answer for question 2, Mr. Ordóñez?
The only variable degree of freedom that we don't know is the phi2.
Is that phi2? Come on.
In the
what's the support? What are the boundary conditions on the right?
And the guided shear force is zero, and the slope also.
The slope is what? How much is the slope on the right?
Is 0.
That's a value that you know. So
yes,
what's the unknown? What's the joint degree of freedom that you need to calculate?
The 2.
The 2, right? Exactly. So so you have 4 degrees of freedom. 2 on the right, 2 on the left. You need to calculate only 1, and that's D2Y. That's the only unknown. The other are known. Okay, let's go to question 3. Okay, if you integrate a delta Dirac times the function f of x, any function, what's the result of that integration? Mr. Barba, what's the result of that integration? Question 3.
When I integrate the delta Dirac in x, for example, in x minus a in position a for multiply for any function, equal since the function evaluate in this point.
Exactly. Evaluated at that point. Okay, so in this case, you have to multiply the polynomials integration n1, n2, n3, and 4 times p of x, okay? And the result of that integration is just each one of these 4 functions, n1, 2, 3, 4, evaluated at the point where you have the delta function. So in this case, you have to evaluate these functions at L over 3. Now, do we need to evaluate all of those 4 functions? No, why not? Because we just said that we need only we need to calculate only one degree of freedom, which is D2y. So what's the only force that we need? F2y. That's all. And finally, what's the form? Okay, what's the mathematical form of the bending moment in beam finite element? How do you calculate a bending moment? Sorry. How do you calculate bending moment, Mr. Iñiguez? How do you calculate bending moment, Mr. Iñiguez? Do you remember how to calculate the bending moment with the displacement function?
No, doctor, I don't remember.
I should hang you and let you in the desert, no water, lots of sand. Come on, fortunately, this is being recorded. If somebody does not remember how to calculate the bending moment in a beam, we're in trouble. We are in trouble. Mr. Barba, do you remember how to calculate? Oh, I already asked you. Let me ask somebody else. Ms. Lopez? Ms. Lopez or Mr. Arias? Mr. Arias, do you remember how to calculate the bending moment from the displacement function?
Yes, doctor. The second derivative.
Exactly.
The second derivative. It's okay.
Could you please tell me the full expression for the bending moment? Complete expression
of the
for the bending moment. It's not only the second derivative. There is something else at the beginning of the expression.
E over
No. No. It's the Young modulus. That's what's the letter for Young modulus?
Yes. The Young modulus.
What?
Multiplicar the inertia.
Multiply it by the inertia, okay, and then
the L over Q.
No.
No.
Well, you just said that it was proportional to the second derivative.
Yes. Sorry. But this is
okay. So that's the expression for the second derivative. Okay. So in this case, remember, finite elements is an approximation. Okay. So my question now is, before we go to question 4, okay, what was the order or the polynomial, okay, to approximate the displacement in finite element? What's the order of the approximation? Mr. Ruiz, do you remember the order of approximation or of the polynomial for the approximation? Mr. Ruiz?
For the bending moment?
No, for the displacement function. For V of X in the beam.
One order.
No. People, I'm really worried. Mr. Jimenez, do you remember the order of approximation of the polynomial of approximation for the bending, for the deflection in the beam bending problem? This is chapter 2. Do you remember?
This function is cubed.
Exactly, it's cubed. It's cubed. So my question now is, let's go now to question 4. What's the form of the bending moment that you would expect? Okay, so you say that the approximation is over 3. That's what Mr. Jimenez said. And Mr. Arias said that the bending moment is proportional to the second derivative, right? EI second derivative. So let's go now to question 4. What's the mathematical form of the bending moment? in the final element.
It's linear.
Exactly.
Linear.
Exactly. So you get 3, order 3 polynomial, and differentiate once, you get second, differentiate one more, you got linear. So you know that it is a line on the left is negative, on the right is positive. Is this very long? Tell me. I don't think so. I don't think so. Any questions about these people? Any questions? See, I'm not going to give you the solution. So you have to sit and do it. If you have problems with the solution, send me an email and I'll try to answer back. I'll try to explain you. If you have more problems, yeah, we can set up a Zoom session. Don't do it tomorrow because tomorrow is Friday, it's 24th. I would like to have a short session in the same similar way as this with the mechanical vibration people, but I'm not going to work in the afternoon. Okay, so next week, yes, I have to work. And if you have any problems with the solution, send me an email and we can set up some meeting. Okay, people, is there any questions about this problem? Okay. Okay, now let's go to the second question. You see the quiz? Somebody, can you see the quiz? I'm going to page 4.
No.
Can you see?
Negative.
No, you're not sharing.
Okay, now. Now?
Yes.
Okay. There it is. I'm trying to reduce a little bit the size. So, oh man, too much. Maybe 90%. It's better. Okay. Okay, so let's see. Mr. Carrillo, would you please read problem 2?
Good morning, doctor. We want to determine the displacement of the right corner of the triangular 0.5 centimeters thinks steel plate support welded to the structure on its left side and
please. There is a point there. So when you see a point, you have to make a short stop and then you continue. Okay, so here you have a point, so you have to stop a little bit. So we have this support, okay? It is 0.5 centimeter thick, okay? Steel. On the left is welded, so you see the sign that it is fixed here, okay? And we want to calculate the displacement of this corner. This is the corner, okay? This is a triangle. So this is the right corner. And so we want to see how much this move, okay? Mr. Carrillo, what do you expect in this structure to be the motion of this point? What do you expect? Can you describe the motion, the displacement of this point?
It's very little displacement.
No, but yeah, but you don't know if it's going to be little because 10 tons, it's a lot, right? The other day we did some tests on the XT faculty and we applied a force which was how much, Genesis? How much was the force that you need to apply on your beams to make them fail?
On the G profile beams, it was 78 kilonewtons.
Kilonewtons. That's a lot. That's about 8 tons. And it's just bang. So you don't need to, I mean, if you tell me that this is not going to move much, please be careful because this is a large force. Okay, so we better wait, okay, and see what we get. But in general, if you tell me that 10 tons doesn't make much to this structure, I doubt it, okay? What else can you say, Mr. Carrillo, about this, the motion, the displacement of this point?
Only in X, doctor.
Why? It's correct, but why you expect to be only moving in X?
Significant.
No. You said it is correct that I expect this point to move only in the right direction, only in X direction. But why you say that? I agree with you, but the thing is, why? Can you explain me why you expect this point to move only in the right direction, in the X direction? Mr. Nevares, do you agree with Carrillo that this point will move only in the X direction?
Yes, because of symmetry.
Exactly. That's the answer. That's the answer. We have symmetry, so everything that happens up happens down. So the best for this is just to move in the X direction, as you said, Mr. Carrillo. You see, you are reading and you are giving a lot of results out of this without writing anything. It's just a matter of thinking. That's all. Let's go on, Mr. Carrillo.
Okay. 10 tons of the force is acting horizontal to the right.
Okay, so this is what we are seeing. Okay, we have this force point to the right. It's 10 tons. 10 tons. Okay, Genesis, what happened in the second test? What was the operator felt for the second test?
He was scared and he might be test on the 68 kilonewtons.
Exactly. So 10 tons is I mean, it's a large force. Okay, let's go, Mr. Carrillo.
In an efficient manner on two triangular elements, discretization is recurrent.
It requires
present some
just a second. So to do this analysis, you see here, that's what we're asking you. We want you to calculate the displacement. We want to calculate how much this point moves. To do that, you have to, in an efficient manner, okay, use two triangular elements. That's the elements that we're being using in chapter 3. Okay? Go on.
Present some checking of the result.
Exactly. So remember, always we have to do some checking. Okay? Okay.
For the triangular plane stress.
No, just a second. Let's go on. How would you discretize this? How would you discretize this? Using two triangular elements. Mr. Zamora, how would you discretize this?
I think that we could have with a cut in the center.
Exactly. It's easy. Exactly. It's easy. See, my exams are never complicated. It's just you that you get complicated. I am not a complicated person. You are complicated. So this is just, I hate MLSists. No, this is a joke, people. You know it, it's a joke. So that's what Mr. Zamora is suggesting you. Okay, and Mr. Nevares said that this is that, or that's what he meant, because this is symmetric. So in an efficient matter, here you have the partition, you have 1 and 2 triangles. And Mr. Nevares said that this point moves only to the right because he said the word that we've been using lately, symmetry. So you have 2 triangles, right? But in an efficient manner, we can only analyze 1. Okay? Now, if we go this, we will analyze this, we have to think about the conditions that we have to apply in this point. But that's all what you need to do. Right now, right now, if you analyze the upper triangle, like this, okay? You need to apply, how much is the force that you have to apply here? Mr. Peralta, how much is the force that you need to apply in this point?
The half of 10 tons.
How much is the half of 10 tons?
500 kilograms.
Come on, 5 tons. Yes. Yes. I don't know, for some reason I cannot write. So let's see if I can do this. There you go. Okay, and the question here is that what happens with this joint? What happened with this other joint? This and that. Mr. Iñiguez, what happened with this joint? What happened with that joint?
Still, the displacement is 0.
Exactly. In X or in Y?
In both.
Exactly. So this point doesn't move, this point doesn't move because they are clamped. And finally, Ms. Lopez, what about this point here, which is this one here? What about this point? What can you tell me about this point here? Ms. Lopez?
This point, I have displacement in direction X.
And what happened in the Y direction?
X. In the X is X. X is X.
What about the displacement of this point in the vertical direction?
Not because the force applied the
No, that's not the reason. That's not the reason. Nevares, what's the reason? What this is 0?
Because of symmetry, it's considered guided.
Exactly. So we said that this point move only in the X direction because this is symmetric. If I want to give you some trouble, okay, I can do this. Okay, forget about this. This is the triangle that I want you to analyze. And in that case, okay, this point will move to the right and will move up. So you don't have symmetry in this case. So the reason why this moves only in the X direction is because it is part of this structure, and with this structure originally is symmetric. So how many unknowns do you have in this triangle problem? How many unknowns do you have in this case? Mr. Carrion, how many unknowns do you have in this problem? Mr. Carrion, are you there?
Yes, doctor.
How many unknowns do you have?
1.
Exactly. Do you think this is a long problem, Mr. Carrion?
Excuse me, doctor. I'm sorry, my internet isn't good.
Okay, Lord. Okay. Somebody else. Mr. Arias, do you think a problem with one unknown is a long problem?
No, doctor. I think it's easy.
It's easy. What's the thing about this? The thing is that you have to sit and think. This is something I insist. You don't like to think, and that's not my problem. That's the key. Okay, let's do a second. Let's do a second poll, a second survey. It's a combination about something about this and a little bit related to the third problem. Okay, so let's take a few minutes to complete this poll and see how we do. Okay, people, do you see the poll? It has 4 questions. So go on, please. So in the first one, so we see that the geometry, immediately we see that it is symmetric. Immediately. So what does that tell you in order to save some time? That's what the first question is about. Okay, if you write something a little bit, do it. That's just practicing your English. So that's easy. Go on, people, come on. I need you to do some work today. This is the last day of the semester, basically. Is there Arias? Did you complete question 1? Would you please turn on your cameras if possible? So at least the last day of class, last day of the semester, I would like to see your faces. See, the problem is that when I go to the university, let's suppose that in May, we can return. To cross with you on the hall, and I'm going to not recognize you. So that's why I need you to recognize you. So question 2 is very easy. We just discuss it.
Yes, doctor. The question.
Now, the third question is interesting. Maybe I should share the. Can you see the question on the other screen now? Let me share the screen. Okay. Can you see the question 2 on the screen, people? People, can you see the screen? The question
Yes.
number 2, the problem number 2?
Yes.
Okay, good. So here you have the expressions for all these parameters which define the stiffness matrix of the CST element, okay? So what I want you to do is, if we consider only this triangle, okay? Why don't you calculate gamma, okay? Gamma for this joint, okay? So I want you to calculate gamma for this point. Now I have the 3 values of gamma here. Okay, so I want you to calculate gamma for this point. Go on. People with me. Let's consider that this point or this joint is I. This is J, and this is K joint. Okay, so I want you to calculate gamma I. That's the gamma for this point. That's the question 3. Okay, in a minute, we will, as a group, we will see how much you get. And finally, okay, since well, not for this one, for the last problem, you need the stress, and for the stress, you need the strain. So here, okay, with this N, you can deduce an expression for epsilon x, okay? That's what I'm asking you in the question 4 of the poll, okay? So you have these functions which help you to interpolate in each element. So I want you to relate this to the strain, and that's question 4 of the poll. Mr. Ramon, did you complete all questions? Mr. Ramon?
Yes, doctor.
Okay. Mr. Jimenez, did you complete all questions? All questions of the poll?
Oh, no, I need
Not yet? Okay, okay. A couple of minutes. Okay, once you're all done, please raise your hand. Okay, so we know how many people have completed the poll. Please, when you complete all the questions of the poll, please raise your hand. Okay, so we can know how many of you have finished. Mr. Nevares, you did not complete all the poll?
I don't know how to answer the last question.
Okay. How do you relate strain to displacement? What's the relationship between strain and displacement? Mr. Nevares, epsilon x is equal to what?
Epsilon x du over dx.
Okay. Okay. And how do you get u, the displacement of any point u, as functions of these polynomials n sub m of x and y? That's what you have to remember. That's interpolation, remember? That's what we do in finite elements. Please, people, all of you who have completed, raise your hand so I can see if you have completed the poll.
Doctor, the second question, we have assumption the specimen with respect to the support, no?
Yeah.
Okay, thank you.
Mr. Ruiz, how are we doing? Mr. Ruiz?
Yeah.
Did you complete it? Yet.
No, 4, no compare.
It's not completed. Okay. Mr. Zamora, are we there? Did you complete the poll, Mr. Zamora?
I complete the
Mr. Arias, how are we doing?
I write the answer the 4 questions.
Okay, go on. Okay, one more, and oh shoot, somebody. 6 person. I have 7 person who just completed. Okay, let's go on. How can you describe the application of symmetry using CST elements? Well, Mr. Nevares said, right, is that the right end doesn't move in the vertical direction. That's the description. And that will tell us something in the next question. So in the next question, everybody is correct. Okay. So the left end, the left edge of the triangle, since it is clamped, doesn't move. The right end doesn't move in the vertical direction. So there is only one unknown, which is the displacement in the X direction. So everybody is correct on question 2. Good. How about the gamma parameter? Anybody? How much did you get for the gamma parameter of the right corner? Anybody? How much did you get, Miss Lopez? How much did you get for the gamma of the right corner? Miss Lopez?
-10.
-10, somebody. How much did you get, Mr. Zamora, for gamma of the right corner? Mr. Zamora, how much did you get gamma?
-10.
-10. Okay, let's see. Can you see my screen on the with the information on the problem? See, this is my I. Let's put it here. This is my I. This is my J, and this is my K.
That's not in the middle.
I'm sorry. You're right. So here I have my K there. So if I want to calculate gamma I, okay, this is the formula that I need to apply. Okay, so tell me, what is XK? XK for this case. This is the way I name it. That's going to be XK.
0.
0, right. And how much is XJ?
0.
0.
So, Ms. Lopez, how much is gamma I?
0.
Exactly. See, I'm telling you this because this simplifies this calculation. So this value here and this value here are 0. Okay? So we know that we need to calculate only one parameter of this K matrix because all the others are 0, the displacement are 0, and we do not need them for this calculation. We are calculating only displacement. So there is only one value, one displacement that we do not know. And for that, we need only one value of the K matrix. And in that K matrix, gamma, this element is 0. So that's going to be a lot of zeros there. Okay? Now, after you do this, it's easy to calculate the deflection of that, the displacement in the X direction. And finally, the last question is related to the strain. Okay, let me go to the last question. Here, okay? With this information, you should be able to calculate, or not to calculate, but to draw something like this. Okay, we have this, that, and we have this. So we got 6 elements, which are this one here. And with this information, you should be able to establish the location of each joint. So all of this is from this part here. Now, we know that these are the displacement. So we see that joint 1 is here. So all of this is clamped. So you have 1, 2, and 3. So that's joint 1, joint 4, and joint 6. They are on this wall, they are clamped. So they don't move, neither nor in X, nor in Y, X or Y. So we need to do a stress calculation in this cut. By symmetry, that's what Mr. Nevares said. This part here supports the same stresses that this region here. So the stress in this triangle is the same as this one. The strain in this triangle is the same as this one. So we need to calculate the stress only in these two triangular elements, here and here. Now, to get there, I need to calculate epsilon x. That was the question. So epsilon x, as Mr. Nevares said, is equal to du dx. Okay. Now, u can be approximated using these parameters. We need to differentiate this with respect to x. And the derivative of this with respect to x, what will give you to? The derivative of this with respect to x. Anybody? What will give you? The derivative of this with respect to x.
A constant.
Exactly. And that constant is equal to beta divided by 2a. So here, that's going to be equal to summation. Beta, let's call it beta m times u sub m, and that divided by 2a. Okay, so we need beta, we need u. What is u? That is deflection in the x direction that you have here. You need to calculate beta, but some of the betas are 0. So some of these terms are going to be 0, and that's it. What do you expect for the values? If you compare the strain in this triangle and in this triangle, what strain do you expect to be larger? This one here or this one here? Anybody? See, I have a, shoot, no, that's not what I need. I need this. I don't know why, but it doesn't. Have any colors. For some reason I cannot write here, but here I have an element, and this one here is element 1, I guess. So this is element 1. Okay. And the next one, I think, is element 2. So I have another element here. There. What do you think? it's going to be if you compare the strains between the strain in element 1 and element 2, which one is going to be larger?
Strain 2.
Why?
It's closer to the concentrated force.
Exactly, it's aligned. And the sign, what do you expect for the sign of epsilon 1 and epsilon 2? Mr. Peralta, what do you expect the sign of epsilon 1 and epsilon 2? So you evaluate this in here and here. What do you expect for the sign? Are they going to be positive or negative? Mr. Peralta?
Yes, doctor. It have to be positive.
Yeah. Yeah, because you are applying a force to the right. So everything I expect to be in tension. You see, that's thinking. That's analysis. That's what we need to do. Okay. Any question, any comments on the solution that we have prepared? Well, we haven't prepared, so it's just a discussion about the solution. People, any comment about this? No? Because otherwise, I'm going to go to the last point of this session. And the last point of this session is to assign the themes for your final projects, okay? Okay, so I'm going to share the screen so you know that I'm not, can you see my Excel?
Yes, doctor.
Okay, so here I'm going to put the number of the group. So I have from group 1, 2, and then here, okay, and here, this is the theme. Okay, and with theme, we have 12 themes. So each one, or maybe we can call it the structure. Okay, so all of these structures have been prepared by Engineer Isaac. So he just gave me a list. I'm going to show you in a minute. So what I'm going to do is just to, by the last time, so these are the values of the random numbers. So I copy them here so they don't move anymore. And then what I'm going to do is going to organize this there. So I'm going to save this, and that's it. So group 1 will analyze structure 9 and so on. Okay, people, this was done randomly. I had nothing to do with that. And now I'm going to open what Engineer Isaac sent me. So you have a rough idea of the topics that you will be analyzing during your projects. Okay, let me. Okay, so remember now, okay, I'm going to publish this, don't worry. And now I just want to give you a rough idea what the structures are. Okay, so for example, the structure 1 is the superstructure of a container ship. Okay, so you're going to have above the main deck, you have several decks. And in each one of these decks, you have load. And the idea is that you model that, apply the load, and determine how much is the stress levels in this superstructure. Okay, that's another structure in between decks in the main in the engine room. Okay, so you have in the engine room, okay, there are some decks between the main deck and the floor, but you cannot have a continuous one because you have the main engine in the center part. So you have some decks, so you have to model that and put some load on it, etc. Okay. Here, for example, structure 11 is a collision bulkhead. Okay, you have to be careful because we don't want just to model the collision bulkhead, but also the structure which is around it. Why? Or the adjacent structure. Why? Because the thing is this, okay, when you analyze a bulkhead, my question is, what are the boundary conditions? And you don't know if those are simply supported or clamped. So what we can do is we can model the bulkhead and also parts of the adjacent structure. And what we can do is we can analyze the three conditions, okay? Simply supported, clamped, and then including adjacent structure. And we can compare and see what are the real boundary conditions and if they are closer to either one extreme, so either close to the simply supported case or to the clamped case. Okay, so that's what you have to do. Okay, so in the next days, Engineering SAC will send to each group the information about the structure that you have to analyze. Okay, so remember, the first part of this, of completing this analysis is to prepare the geometric model. Okay, for the geometric model, you have to use what program? What program do you have to use for the geometric model? Rhino. Yes. And that's easy for you since you have experience using that in the 2 previous classes. Okay, once you prepare that, you import it from ANSYS. And in ANSYS, you start converting the geometric model into a structural model. To do that, you have to consider thicknesses, you have to consider material, then you have to implement boundary conditions, the supports of the structure, then you have to apply load, and then you start seeing what are the deflections, what are the stress levels, if they are close to the maximum allowable values, things like that. That's analysis, okay? So my suggestion is that you get together with your group and try to start thinking about how are you going to organize this work, okay? Any questions about this, people? Any questions?
Doctor,
yeah.
My group was for the exam was group number 11, and it has changed to group number 7 when we going to the presentations this week. Are we 7 or 11 now?
Don't worry. Let me share with you again. Can you see my Excel table?
Yes.
Okay, this on column L, these are the official number of each group. Okay, so you are, where are you? Where are you? Where are you? Oh, here it is. You are group 11. So remember, in the first part of the class, you organize the groups, but I asked you to do some changes in order to include more diversity in each group. So after that, these are the official number of each group. And yeah, a good question. I'm going to See this that you see here, this is the order of the presentations of the previous project. This is what we did yesterday. So I'm going to include the same information here, and I'm going to include the structure number, a short description of that, and I'm going to give it to you. So we are sure that everybody knows that what group he is in or out, he or she is in, belongs to. Any other question, people?
The correction you made, you did as well as comes with presentation again?
No
presentation.
No, that's enough. Yeah, the correction that Mr. Nevares, it's a good point. Let me, okay. This is something that we have seen that happens when you have some parts, for example, in this case, for example, let's suppose I have a partition like this, okay? And I include one joint here. Here, in something like this. Like that, okay? What's the problem? The problem is this, in this element, okay? The function is interpolated using this value, this, and that, but does not consider this value here. So if you have this value, let's suppose I have this value, the displacement of this point. Let's suppose this displacement is a little smaller, and this one here is like this one. So we interpolate like that. There. So this value here is the displacement of this joint. This vertical value, displacement of this, and this little is displacement of that. Now, let's go to this other element here. Let's change color, green. Now, the value of this is the same, but the value of this is not here. So let's suppose this is negative, okay? And the value here, let's suppose is small. So the displacement for this element is from here to there to here. And you see that here we have a hole. There is no continuity in displacement. So you have the displacement here, goes up to here, and then you have a jump, and then you have something different. That happens when you have this situation. So in this case, what I asked your classmates was to correct this. And what you can do in this case is just include a partition like this. So instead of having one element, you're gonna have one and two elements. And in that case, this point here will be common to these two, and you will have continuity in displacement. Okay. Any questions about these, people? Please, any question? No questions. Okay. Anything else? Anything else? No. Next week.
Doctor,
Yeah.
I'm sorry.
Go on.
I have a question, but about the assignment number five.
Okay.
Yeah, I have checked yesterday the assignment, and I don't understand so good the question number one about the answers analyzed. Could you please explain me?
Let's see if I can. Okay, let me erase this. Okay. See, the thing is this, okay? when we want to model an structure like the one I gave you. So let's suppose I have, this is a side frame in the bottom, something like this. And let's suppose I have some several decks like this. Here, this is the floor. Okay, so let's include one more deck like that. So you want to model this, okay, here you have the pressure, here you have the weight, and so on. So in this case, what I want you to model is from this point, okay, you don't have to analyze. All what you need to do is to prepare the model from here and do all of this model. So for that, you need to model all this part here with frames. Okay, it's beams, but also they include the axial effect and torsion. That's what I need to do. So this is a frame structure. Now, for the second part, what I want you is to do the next step. The next step is only up to here, because it's just too much. Okay, so I want you to prepare a model of this. So here we have several frames and like that. And this here is going to be here. Okay, but only up to main deck. So this is a model using only frame elements. And this is another model using plate elements. Okay, so here you have something like this. But here you have only elements between two joints. So this is problem 1, this is problem 2. Mr. Carrion?
How many frames in the model do you expect?
Yes, that's other question. How many frames?
That's, see, what's the idea here? The idea is that I want you to practice. Okay, let's suppose that you say that the module is 3 meters long, 4 meters long. I don't mind. The thing is that you practice. To do that, what do you have to do? You have to draw that and you have to extrude it, right? Do it. Then don't include 1, include 2, 3, 4 frames. What do you have to do? You have to take that and you have to split it. Do it. If you do that, you're practicing. If you put 5 instead of 4 frames, I don't mind. Okay. For the thickness of the hull, okay, you have to use 8 millimeters, and you make a mistake. Instead of 8, you use 9. I don't mind, because what we need you to do is to do the process, to practice this. This is not analytical. This is just practice. So if you when you graduate and you need to do this analysis, what you need to do? You have to do this, then you have to do that. And in that case, yes, you have to consider exactly the amount of frames that you have in the ship. Okay, take it from the plane, from the plan, or go and measure. So you have the spacing between frames. The thickness, go and measure the thickness. What is the thickness? It's not 8, it's not 9, it's 10. Okay, put it 10. But you know how to do it. Okay, so invent it. That's it. Now, don't be so lazy. Okay, okay. Don't include only 1 frame. Include several. What we need you to do is practice. Okay, this is a first step, and then the project will demand a lot of effort. So this is a good first step, and then you go to the project. And after that, yes, you can take basically more complex structure. If you do not something, you can look it up and complete what you know, and you go on. But the thing is that you need to practice these things. Engineering SAC prepared a very nice file or document explaining the steps. The thing is that you need to sit and do it. That's what we need to do. Mr. Carrion?
Yes, doctor. So in the question one is just the transversal view. Is anymore just not in 3D. In the second question is in the 3D view. Okay. I got
it. The thing is this is which is very interesting. Okay, in the previous programs, see, I started using finite elements in 1990, 91 or 92, and we have to define the characteristic of these elements, the transfer section. In this case, in the first problem, you need to define the transfer section. Okay. This element, this is a beam, right? This is a beam. But the element has a section. So the section is going to be something like this, a plate. And here, you have something like that. Now, this is the section. To define that, from here to here, that's the spacing between frames. You have to include the height of the web and the width of the flange and the thicknesses, of course. So you have to include this for these elements, yes. But Engineer Isaac explained how to do this, right? You select the section and then you start inputting all of these dimensions. And then you have the section completely defined for the element. Still, you see something like this, but this is a plane analysis. Okay, the elements are beams, which are defined between joints, but the sectional properties were calculated internally once you define the section of the beam.
Should we include brackets in the second question?
If you want, yes, that's a good idea to practice, because in the real world you have a very large number of brackets. Yeah, that's a good idea to practice. Yeah, it's a good idea.
Doctor.
Yeah.
If the question one is just a 2D view, the formula of the spacing, how I use it?
Because that's the flange, the width of the flange.
But I will use this in the question one or the question two?
In both.
Both ones.
Yeah, because from here to there, that's the spacing. So this is the, where am I? Here am I. This is the section for one beam. This is the spacing from here to there. This is the spacing. And this is the spacing. So you are modeling here this as a group of beams in here. This is a much better model, of course. But the problem is that to do this, you need much more time than for this. Yeah, even though you see this in 3D, this is basically a plane analysis. Okay, all these frames are beams. Okay, so you do not consider the bending of this plate. You consider the bending of the beam as a whole. So this is the section that you consider. So with this here, internally he calculates the inertia, but in this case, the inertia is calculated in two directions. So you have to calculate the inertia in this direction and the inertia in that direction. You also calculate, so inertia in Y and Z. So you have the polar moment and the area for shear in Y and Z. All of this out of this information.
Doctor,
Okay.
and this spacing is for the two decks. Is the same or?
Okay, the spacing I'm talking is between frames.
Yes.
From this frame to the next one. I don't know what the deck has to do with spacing. Okay, what I suspect is that when you do this, so you will have something like this. This frame here will come up to here, and then you will have something like this. So this spacing here is going to be the same as in here. Is that your question?
Yes, and the upper
because
deck,
you try to form a continuous ring. Yeah, probably the same. The spacing. I would. That's what I would do as a designer. So this frame here, make it continuous all along this structure. Probably the size will decrease because the load will be smaller in this area than in this area. But it's going to be continuous. If you want, you can draw this with all of this material, not only up to the main deck, but also to the upper deck if you want to practice.
I don't know if you are trying to eliminate the inner bottom when you draw.
In this case, the inner bottom is not considered because this is like a solid plate. It's very rigid compared with the frames. In this case, yeah. In this case, you have to include it.
In that, yeah.
In this case, in the second, yes, you have to include it because it's part of the model. Okay, in one of the projects, for example, you have to analyze this, right? What are the bundle conditions here? We can say that this is clamped, but is it real clamped? I don't know. What do we have to do? We have to go like this. So you want to analyze this frame, you model that, and if this is strong enough, that will be very close to being clamped. But that's what a good idea to model the whole thing and then compare with this case. And then you have a very first experience on modeling this as clamped. In some cases, it is really useful, model that as a clamped, because this analysis is much easier than this one. But if you have doubt, well, the only choice that you have is to model the 3D, complete the structure, and then you do the analysis. Okay, my suggestion, people, is to get together next week in a very informal way. Could be Wednesday or Thursday, something like that, to check, to see what you have done so far. Okay, if you have doubts about the structure or something like that, then Engineer Isaac can tell you something back. Okay, if that's correct or not. In some cases, you see that I give you a plan of a ship, right? You see the plan, and it's sometimes it's difficult to understand how the elements are connected and all of that. So if you have doubts, we can get together next week. I'm going to set up a meeting, and I would like to see what people have done so far, because I don't want anybody to get behind. Okay, people, if there are no more questions, then I'll see you next Wednesday. I'm going to publish all of this information in the Aula Virtual, in the site web, so you can know what structure you have to analyze. And yeah, my suggestion is sit and do the solution of the quiz. I see many doubts, and that's something that I don't like. So my suggestion is do it. I'm not going to give you extra point for that, no. But my suggestion is you have to learn. Okay, people, is there any other questions about this?
I want to tell you that I have a little bit problem with my ANSYS because I update my software and it doesn't work. The ANSYS 2021, but I am working with the version 17.2 because it doesn't work.
The problem is this, okay? You can hand me anything you want. See, you do supposedly you do an analysis, print something, and bring it to me and say, this is my analysis. But you can take these figures from the internet. The only way, just a second. The only way we can be sure that this is really what you have done is to do checking. When you present the final project, you give us your model. And I'm asking Genesis and Engineer Isaac to run the model. And you say, for example, you report a deflection in this point of the order of, I don't know, 20 millimeters. And I want them to do a quick check. That's the value that your model really gives me.
No.
And the problem is that we need to have the same version. That's all.
I think that you don't understand me because I say that my ANSYS 2021 doesn't work in Windows 11. So I was searching in the web and says that it's really ANSYS 2021 doesn't work with Windows 11. So I try to use, so I can show you that it appears.
I don't have the time. If you don't have problems with that, you talk to his engineer Isaac. He's the one to talk. But please sit in my chair. If I'm going at the end of the semester, I'm going to give you a pass or fail that depends on that you show me that you indeed have practiced enough using ANSYS. And the problem is that we have to check. Okay, so that's why we insisted. And this is not new. Everybody listened to the presentation by Engineer Isaac. We insisted we have to use the same version of the problem because we need to check. There's going to be a lot of problems, okay? And you come to Isaac and say, I have this problem. Okay, let me run your model in my computer. If there are different versions. So the only way is that we uniform. We use the same version, and that's what we are doing. Remember that we as a university, we have the license, so we're fine. We as a university, we are doing what we have to do. We had the license, we renew it during this pandemic, so we are with the law. But everybody needs to be in the same path. Please try to use these days, which you don't have classes, in order to solve that problem. Okay. There are some options. Okay, I don't know if it can be done, but eventually one of the possibilities is that you connect yourself with one of the computers in the lab. Okay, but the problem with that is that I live relatively close to the university. And I have that problem too. So sometimes I need to run ANSYS in the computer in the university, but you have some rains and things like that. So electricity stops and somebody has to go to the university and to my office and turn those computers on. And the problem is that sometimes there's nobody who is going to university. And so that's a big problem. But please, during these days, try to solve that problem. Okay? Because you need, I want you to put many hours practicing. Anybody else? Anybody else? No? Okay. Then Feliz Navidad. Abracen a sus papás de mi parte. Bye-bye.
Thank you, doctor.
Well, doctor, feliz Navidad.